Welcome to the deep dive. You know, usually when we talk about a medical diagnosis, there's this expectation of like absolute precision, almost like engineering.
Right, yeah. Like it's just binary.
Exactly. You break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
Broken or not broken. I mean, it's clean, and frankly, it's comforting. We really like things to be visible and, well, perfectly categorized.
We really do. But the second you step into the world of actual human biology, into the reality of modern medicine, that x-ray machine suddenly feels completely inadequate.
Yeah, it really falls short.
Because we're looking at a diagnostic landscape that is incredibly messy. It's moving, it's complex. And that mess is exactly what we're getting into today. We are diving into a stack of 20 brand new cutting-edge medical AI papers to see how technology is trying to map the chaos.
And our mission today is to give you a full spectrum view of these sources. We are going to track how artificial intelligence is evolving from being just a simple diagnostic assistant, a tool that essentially just looks at a picture, into an autonomous, longitudinal, and biologically aware system.
Which is a massive leap.
It is. We're covering everything from computer vision in crowded, chaotic hospitals to AI agents that actually design microscopic molecular drugs from scratch.
It's a massive stack of research we've got today, but we also have a special constraint. To strictly respect your time as a listener, we are putting a timer on this audio overview. We will end within exactly 15 to 17 minutes.
Right, no fluff, just the most critical insights.
Exactly. And just so you don't get lost in the weeds with us, we have a strict formatting rule today. We will explicitly mention the paper number before we use or quote any of our sources.
That structure is going to be vital because we're covering a lot of ground, and we really need to start with the most basic challenge, which is how AI actually perceives the physical world, the vision problem.
Right. Because AI has gotten really good at flat 2D images. But human biology is 3D, it's messy, and it's constantly moving. Which, brings me to a great real-world parallel.
Oh, yeah.
If you've ever tried to take a picture on your phone of something really close up, like, I don't know, a bug on a leaf, the camera just keeps hunting for focus, blurring in and out.
A classic depth of field problem.
Yes.
And that depth of field issue is exactly what they tackle in Paper 7. They look specifically at microscopic urinalysis. When a technician puts a urine sample on a glass slide, it isn't actually perfectly flat.
Right, it's not just a 2D surface.
No, it has a multi-layer structure, so all the cells aren't in focus at the same time. You can't just snap one picture.
So what do they normally do?
You'd normally have to snap dozens of individual pictures at different microscopic focal planes, which, as you can imagine, takes forever. But Paper 7 introduces a brilliant, practical solution.
Okay, I'm listening.
Instead of taking a bunch of static photos, the technician just takes a single continuous video for 2 to 14 seconds while manually turning the focus dial by hand.
Oh, I love the simplicity of that. But how does the AI actually use a blurry video?
Well, in Paper 7, the AI breaks that short video down and performs real-time focal stacking. It analyzes every frame, extracts only the pixels that are sharply in focus from each layer, and mathematically reconstructs a single all-in-focus composite image.
Wow.
Right. And once it knits that perfect image together, it applies deep learning to detect and classify the urine sediments. It takes a tedious manual task and streamlines it for the real world.
So we go from microscopes fixing blurry slides to something even harder, which is tracking the human heart.
Oh, yeah, a massive jump.
Right, because in Paper 17, the authors introduce MCFnet. They look at echocardiography to localize myocardial infarctions or heart attacks. And a beating heart is the literal definition of a moving target.
And tracking that motion is where things get highly complex.
It is. But what blew my mind in Paper 17 is this concept they use called sparse supervision. I literally had to read this twice.
It's pretty incredible.
The AI uses just one annotated template frame to track the cardiac motion across entire ultrasound videos. One single frame. And it still achieves a 72.4% F1 score.
And to put that F1 score in context for you, it means the AI is doing a remarkably balanced job of catching the true abnormalities without, setting off a bunch of false alarms.
But how does it do that with just one labored frame? I don't get it.
It relies on optical flow. Basically, the AI learns the physics of how the pixels are moving from that one anchor frame, and then it extrapolates the motion of the heart muscle through the rest of the video.
Oh, that's smart.
Yeah, it isn't demanding thousands of perfectly labeled images from tired doctors. It's learning to follow the motion from the bare minimum of human input.
That is amazing, but it raises a huge real-world issue for me. What happens when you take that brilliant, highly trained AI and install it in a completely different hospital, like a hospital with older MRI machines, different fluorescent lighting, a totally different patient demographic?
Right.
I'd imagine the AI suddenly feels like it's driving a rental car in a foreign country, Nothing feels quite right.
In machine learning, we call that distribution shift. The data the AI was trained on just doesn't match the data it's seeing in the real world. And in paper 15, they address this head-on with a framework called CRISP.
My first thought was, wouldn't you just retrain the AI for the new hospital?
You could, but retraining takes massive amounts of time, money, and computing power. What's fascinating about paper 15 is that it uses frozen weights.
Meaning they don't change it.
Exactly. They don't retrain the core model at all. Instead, it relies on the stability of probability rankings.
Walk me through that. What is a probability ranking?
Think of it like this. Even if the new hospital's MRI images look slightly fuzzier or darker, the AI's internal ranking of what is most likely a tumor pixel versus a healthy tissue pixel remains proportionally stable.
Okay, yeah, I see.
So by mathematically exploiting that stable ranking, paper 15 adapts to the new environment. They managed to reduce error margins, specifically a metric called the HD95, by up to 38.9% across different hospitals.
Wait, what actually is an HD95 metric?
It stands for Hausdorff distance. Basically, if the AI draws a digital boundary around a tumor, HD95 measures how far off the absolute worst 5% of that drawn line is from the actual true edge of the tumor.
Got it.
So shrinking that maximum error margin by nearly 40% without retraining the model, I mean, that is a massive leap for patient safety.
Okay, let's unpack this further, because we've really only been talking about 2D images and videos. The real jump in medical imaging is 3D, right? CT scans, MRIs, these are massive volumetric files.
They are. And that 3D frontier is historically difficult because we just lack paired 3D image and text data sets to teach the AI.
It's just too much data to label by hand.
Exactly. But in paper 2, researchers used multiple large language models working together to create a 3D MRI text data set specifically for brain oncology, targeting gliomas and meningiomas.
Wow, so the AI is making the training data.
The LLMs basically acted as a team of synthetic doctors, collaborating to generate and rigorously double-check medical reports for these 3D brain scans.
That is wild. And then in paper 11, they take that 3D reasoning even further. Because it's easy to look at a flat photo, but imagine a radiologist flipping through a stack of MRI slices one by one, tracking a blood vessel as it moves through the tissue.
Right, it's a completely different cognitive task.
Exactly. So paper 11 synthetically decomposes 3D scans slice by slice to create a chain of thought for the AI.
Which is crucial because it's literally teaching the AI spatial reasoning step by step. It forces the model to explain its logic as it moves through the depth of the body, exactly like a human expert tracking an artifact across multiple slices.
But even with perfect 3D reasoning, there's like a trap here. An AI might spot a weird mass in a scan, but doesn't know where that mass actually lives in the body.
Ah, context.
Yeah, that's the gap. Paper 4 and paper 14 are trying to close, moving from just spotting bad pixels to actually understanding human anatomy.
Yes, and it's just not enough to look at a whole CT scan and output abnormality detected. In paper 4, a framework called OKACT structures free text medical reports into a strict organ hierarchy.
How does that help?
Well, by forcing the AI to build a mental map, understanding that a shadow belongs specifically to the left lobe of the liver, not just the general abdomen, it hit an 84.9 ARRC on the CT rate dataset.
And just for context, an 84.9 ARRC essentially means it has near expert accuracy in distinguishing between healthy and diseased patients.
Exactly. And paper 14 tackles this anatomical complexity using something called OCPCT. They use a mixture of experts architecture.
Mixture of experts.
Yeah, so instead of one giant neural network trying to understand the whole body, it routes specific image and text tokens to specialized subnetworks based on latent radiological patterns. It's like a hospital routing a patient to neurology instead of cardiology based on their symptoms.
Man, it's getting incredibly granular. But I think we need to ground this excitement with paper 1.
Oh, absolutely.
Because paper 1 looks at gastrointestinal endoscopy and basically issues a massive reality check. We cannot just chase high accuracy scores on leaderboards. We need explainability.
Right. Black boxes aren't good enough in medicine.
Exactly. If an AI points to a blurry spot on an intestine and says cancer, it has to show its structured reasoning so the human doctor can actually trust it.
And why does this matter to you, the listener? Because faster, more accurate, and explainable 3D scans mean less waiting for a terrifying diagnosis, no matter which hospital you go to. It really democratizes expert-level radiology.
I completely agree. But, diagnosing a single scan is just one moment in time. You get the scan, you get the result.
Seeing the problem is only step one. The real challenge of medicine, the grueling part, is managing a patient over time. Which brings us to the next massive shift in these papers, which is autonomous clinical agents.
Oh, I am so excited about this part. Let's look at paper 3, which introduces 𝗫𝗄𝗃. Now, I do have to push back a little here because I am naturally skeptical.
Okay, let's hear it.
We always hear about AI passing medical board exams on paper. It's a great headline, right?
Yeah.
But can an AI actually run a bustling, chaotic hospital ward?
According to the data in paper 3, it actually can. 𝗵𝗽𝗽𝗵𝗵 didn't just take a multiple-choice test. It managed real musculoskeletal care pathways.
But how does it even do that in real life?
It autonomously retrieves real-time imaging, pulls lab results as they come in, reads pathology data, and then mathematically converts those evolving patient states into concrete clinical decisions.
What kind of decisions?
Like, should this patient be discharged? Do they need a different pain medication? And the results are staggering. It was compared against 81 real orthopedic physicians and actually surpassed experts who had 25 years of experience.
That is wild to me. It's not just suggesting things, it's actively coordinating.
It increased full chain management success by 10.6% and managed 8,240 inpatients over an 8-month randomized deployment. It even increased the cumulative cases handled per bed by 9.7%.
Wow.
It is actively coordinating complex longitudinal care.
But how does an AI remember you over a timeline like that without just drowning in old, irrelevant data? Like if I broke my leg 5 years ago, you shouldn't treat me for a broken leg today.
Right, you need dynamic memory.
Exactly. So in paper 13, they introduce 𝗪𝗪𝗪𝗪, which solves this by giving the AI a self-evolving longitudinal memory.
And the architecture of that memory is fascinating. It explicitly separates general static medical knowledge from your private, changing daily routines.
So if you change your diet or start a new medication,
𝗪𝗪𝗪𝗪 induces those specific updates into its profile of you while isolating and protecting your private data from the core public model.
that makes a lot of sense.
Yeah, and by organizing memory this way, its accuracy on longitudinal support probes jumped from a measly 0.2% all the way to 45.7%.
But to manage that kind of care, these agents need to actually read your clinical notes. And anyone who works in healthcare knows that doctors' notes are, well, they're historically a disaster of messy, unstructured text.
Oh, definitely. Abbreviations, typos, shorthand.
They are notoriously difficult for standard algorithms to parse. But in paper 5, they detail a system called 𝗵𝗽𝗽.
Right.
𝗵𝗽𝗽 is a multi-agent system that runs entirely on local hospital infrastructure, which is great because it means your sensitive data never leaves the building to go to a cloud server.
That's a huge privacy win.
And what's amazing to me is that 𝗵𝗽𝗽 writes its own prompts to extract symptoms from these messy notes. It doesn't need human engineers to constantly fine-tune it.
Really?
Yeah, it managed to extract 72 different symptoms with a 0.95 specificity.
And specificity is key there. A 0.95 specificity means the AI rarely cries wolf. If it says a symptom is in the notes, you can be highly confident it's actually there.
That's incredible.
Think about how often you have to repeat your entire medical history every time you see a new specialist. These autonomous agents from papers 3, 13, and 5 are the exact technology being built to solve that frustration. They remember you, they extract the vital details automatically, and they manage the timeline.
So what does this all mean? We have to ask the elephant in the room. If we're giving AI this much autonomy to manage care and read histories, what happens when it makes a mistake?
Because a mistake in a hospital ward isn't like a typo in a marketing email, it's life or death.
Exactly, which is exactly what paper 12 tackles with MedFailBench. Historically, we test AI simply by asking if it knows the correct answer, pass or fail.
But paper 12 asks a much more nuanced question. Which safety boundary failed?
Right, the anatomy of the failure.
Exactly. If the AI gets a patient scenario wrong, did it simply miss an urgent escalation? Did it authorize an unsafe remote dosage of a dangerous drug?
Both bad, but very different.
Or, worst of all, did it totally hallucinate and fabricate a lab result that doesn't exist? MedFailBench categorizes errors by severity and gate type so engineers can understand exactly how the model is breaking down.
Which is terrifying, but absolutely necessary. And speaking of testing vulnerabilities, paper 6 is essentially a hacker evaluation for AI. I found this fascinating.
Oh, I loved this one.
Right. They gave frontier AI models the task of autonomously hacking and auditing other clinical prediction models.
And how did the different models perform?
Well, in paper 6, Claude Sonnet 4.6 and GPT 4.1 got perfect scores auditing the systems, finding the vulnerabilities, and the cost was absurdly low, like $12 and $8 a run.
That's basically free in medical research terms.
But GPT 4.0 actually failed 39% of the time. Not because it wasn't smart, but because of coding errors and premature session terminations. It basically just crashed. It shows that while these models are incredibly powerful, their reliability in autonomous loops is still, highly variable.
And that variability is exactly why Paper 9 is so crucial to the safety discussion. Paper 9 introduces MamaBench, which focuses on maternal and child health, and they rigorously measure something called the bias trap rate.
Okay, a bias trap rate. What does that actually mean in a clinical setting?
Let's say the AI diagnoses a standard clinical case perfectly. The bias trap rate asks, Well, if we give the AI a counterfactual case, a patient profile that looks clinically identical on the surface but has one fundamental difference requiring a totally different intervention, will the AI fall into the trap of lazily recommending the original treatment?
So it's testing if the AI is actually thinking or just pattern matching.
Precisely. And in paper 9, they found that base accuracy vastly overstated robust accuracy by up to 28 percentage points in frontier models. When pushed with counterfactuals, the AI stumbled.
That's a huge drop.
It is. However, they introduced a method called EARG, or Evidence-Anchored Retrieval Augmented Generation.
Which basically forces the AI to anchor its decision to cited medical evidence before it's allowed to generate a final answer, right?
Okay.
Which significantly reduces that trap rate.
Yes, exactly.
And finally, in this safety segment, Paper 8 tests AI in the messy real world with 𝗵𝗽𝗶𝘀. They gave AI first-person point-of-view videos from visually impaired individuals navigating streets.
And how did it do?
The AI could answer static questions about the video fine, but it struggled immensely with proactive reminders.
Because understanding context in a static moment, like identifying a crosswalk, is very different from predicting immediate physical danger.
Right. The AI couldn't anticipate navigation-critical events in real time. It couldn't see that, like, a low-hanging branch was swinging into the frame and proactively warn the person to duck.
Wow.
These benchmarks, papers 12, 6, 9, and 8, they are the rigorous driver's tests that AI must pass before it's allowed to operate on us or our loved ones.
Yes. And if we connect this to the bigger picture, we've spent this whole time looking at macro-scale problems: hospitals, patient histories, safety gates. But what if AI fundamentally rewrites how we understand biology at the absolute microscopic level?
Here's where it gets really interesting.
Mm-hmm.
In paper 18, we look at single-cell biology with a model called 𝗪𝗏.
Right.
Now, usually AI treats single cells like text. It acts like a language model reading a sequence of genes as if they were words in a sentence. But paper 18 flips that entirely. It treats cells like images.
Which is a profound shift in perspective, but I mean, how do you take genetic data and turn it into a picture?
In paper 18, they took 72 million human cells and mapped them using something called optimal transport. Imagine taking a massive unreadable spreadsheet of genetic data and mathematically forcing it into a grid based on which genes interact with each other.
Okay, I'm visualizing that.
Suddenly, a cell isn't a list of numbers. It looks like a topographical map. Genes become textures. Co-expressed genes become spatial neighbors.
So the AI can just, look at the mountains and valleys of this digital map to see what kind of cell it is.
Exactly. By rendering the cell as an image, 𝗪𝗏 becomes the absolute most accurate cell type annotator out there, and it doesn't even need human fine-tuning. It's using computer vision to intuitively understand the fabric of our biology.
That is wild. And moving from single cells to entire neural networks, paper 19 explores how we read brain activity. Paper 19 introduces 𝗵𝗽𝗀𝗀, a framework that leverages self-supervised learning to decode neural spikes.
Okay, neural spikes.
What's fascinating here is its versatility across species.
Right. It works on motor cortexes in monkeys, vision tasks in mice, and even human speech.
And it does this using masked autoencoding. It takes the electrical storms in the brain, hides portions of the data, and forces the AI to predict the missing pieces.
So it's filling in the blanks.
Yes. This makes brain-computer interfaces vastly more efficient, allowing us to decode brainwaves even when we have very limited labeled data.
But what if the AI goes beyond just reading data and actually starts writing the laws of nature? Because in paper 10, they introduce 𝗵𝗽𝗀𝗀. This is an agentic system that automatically discovers the mathematical laws of biological systems all by itself.
It's an automated scientist.
Now, as a skeptic, I have to ask, how do we know it's not just hallucinating complex math?
That's the beauty of 𝗵𝗽𝗀𝗀. It is specifically discovering ordinary differential equations, or ODEs. ODEs are basically the math of how things change over time, like how fast a tumor grows or how a virus replicates.
Okay, so it's grounded in real physics.
Right. 𝗵𝗽𝗀𝗀𝗀 acts as an automated scientist. It proposes the math and then rigorously tests those equations against real biological data to see if the math accurately predicts the outcome. It figures out how the biological system actually works mechanically.
Which brings us to the ultimate application of understanding all those mechanics: designing new treatments. Paper 16 and paper 20 show us the new frontier of drug discovery. Paper 16 introduces 𝗪𝗈, a framework for molecular design that finds promising chemical hits using only 1/10 of the normal computing power. It's a massive leap in sample efficiency.
And then paper 20 takes those computational efficiencies and builds real drugs. Paper 20 introduces 𝗠𝗲𝗏, which uses diffusion models to design 3D molecules.
How does a diffusion model actually design a drug, though?
Using a diffusion model here is essentially like watching a digital sculptor start with a chaotic block of clay, like pure noise. The AI slowly chips away the noise step by step until it is left with a highly specific 3D molecule that perfectly molds to the target protein's binding pocket.
It's actively sculpting the cure.
Exactly.
And what blows my mind is that this isn't just theoretical modeling. In paper 20, they actually synthesize real-world inhibitors for specific proteins like PD-L1 and CSF1R based purely on these AI designs. And they perform successfully in actual lab tests.
We are witnessing the entire scientific method from understanding the cell to discovering the mathematical equations of the disease to sculpting the exact molecule to cure it being accelerated by artificial intelligence.
It is truly breathtaking to step back and look at the spectrum we've covered today. From paper 7 reconstructing blurry urine samples from a simple hand-turned video, all the way to paper 20 sculpting novel cancer drugs from scratch.
It's a whole new world.
And looking at the clock, we have successfully mapped out the 20 papers, and we are right on schedule, strictly within our 15 to 17-minute window.
Before we wrap up, I want to leave you with a final synthesis to consider. We've looked at these 20 papers in isolation today, but the real paradigm shift happens when we combine these technologies.
Oh, yeah.
Are we looking at a near future where a single unified system does it all simultaneously? Imagine an AI that reads your 3D MRI using the organ hierarchies from paper 4. It recognizes a tumor. It immediately uses the equation discovery from paper 10 to map that tumor's biological trajectory over time. It then triggers the diffusion models from paper 20 to sculpt a custom 3D molecule specifically to fight your unique tumor.
That is incredible.
And finally, it hands that entire protocol over to the self-evolving agent from paper 13 to manage your day-by-day recovery over the next 5 years.
The boundaries between the radiologist, the research scientist, the pharmacist, and the primary care physician aren't just blurring. I mean, in that scenario, they are entirely dissolving into a single intelligence. That is the messy, complex, and incredibly hopeful reality of where this is all heading. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and we will see you next time.